Okay, I just click go live. And if you guys find any problem, don't just talk. Just post a message, right? Because right now, speaker also share the same channel. All right. So it sounds like right now we are here. Hello, everyone. Can you guys all hear me? If you guys encounter any problem, like feel free to leave the message in the chat. Everything good? Anyone want to respond to me? All right. So, okay, I'm gonna start WebHack opening. And today is our first time for WebHack doing online events, online live stream events. And because of the COVID-19 situations, right now we have to move all of our events online. And we also plan to have another event next month as well. We already found our speaker, so we'll keep you posted. And here is our agenda. So from 7:40 to we're gonna have Anton give us a gentle introduction to Scala and functional programming. And after that, we're gonna have 10 minutes Q&A. And if you guys want to leave longer, we can have some networking, things like that. And otherwise, you can call your night. And this one is our HackMD. We're gonna use it for collaborative notes. So if you want to take notes with us, you can just click this link. Yeah, I'm gonna give you 10 seconds to type the link. Is it enough? Okay. And if you cannot get access to this link, we're gonna post it in our live chat as well. And next, we're gonna introduce a bit about WebHack Meetup for some newcomers. And what we are trying to do is we host this meetup like every month at different offices. But during current situations, we move everything online for sure. And we cover all kinds of topics. And we already hosted like over 32 events. We have more than 1,400 attendances. And in our community right now, we have over 1,000 members as well. And if you want to follow our information, you can follow our Twitter. And we also start having our YouTube channel. So feel free to subscribe to our YouTube channel. And we have something new. Right now, we start doing our weekly newsletter. And the first one is curated by one of our co-founder, Fangda, and her engineering manager, Dong. And both of them are working in Indeed. One as engineering manager, the other is a senior engineer. So if you want to subscribe to this weekly newsletter, feel free to scan this QR code. I'm gonna give you another 5 seconds. Okay. And without further ado, I'm gonna introduce our first speaker and the only speaker, Anton. He's right now working in Rakuten as an application engineer. And today his topic is about a gentle introduction to Scala and functional programming. So I'm gonna bring Anton to a stage right now. That's okay. Slides, opening slides. Okay, I guess right now, Anton, you're online. And let's welcome Anton with like big round of applause.
Right.
Okay.
Thanks,
And,
Michael.
Yeah, feel free to start. Here you go.
Right. Hello, everyone. Welcome to a general introduction to Scala and functional programming. I'm Anton. I'm, well, a functional programmer. And since my very first programming job, I've been using Scala for both my personal and work needs. Currently, I'm an applications engineer at Rakuten. And after this presentation, feel free to find me on Twitter, Telegram, and GitHub by the username given on this slide. This presentation is also available online on these links. Feel free to take a screenshot and follow up on this later. Here is our agenda today. My main goal would be to introduce Scala as a programming language. And to do that, I'll give you some examples of universal functional programming constructs and show you the benefits of those constructs. In the end, I will try to compare Scala to some other languages. So the main question is, what is Scala as a language? Scala was created around 15 years ago by one of the core designers of Java's generic system, Martin Andersky, because he was not happy with the direction in which Java was going. And this quote is taken directly from the Scala's website. Scala combines object-oriented and functional programming in one concise, high-level language. As many of you are mostly familiar with the object-oriented part, let's go over to the functional program. So the question is, what lies at the core of functional programming? Is it the absence of side effects in computations? Is it function composition? Is it perhaps immutable data or mathematics and abstract algebra? The answer is quite simple, all of it. But these features can be imitated or straightforwardly implemented in other languages, mainly in Perl. So what's the key difference between Scala and those languages? I would define that functional programming is a way of solving problems which centers around combining side effect-free constructs in a declarative manner. Meaning that functional programming is not a straightforward programming paradigm, but rather something coming from mathematics. Side effect-free constructs is something that ties functional programming to mathematics. It is essentially a block which functional programming takes to build programs. And declarative manner is a way to express this way of solving problems more easily and concisely. To give you an example, consider these two programs. On the left, you can see a program written in imperative style. It mainly focuses on how we can achieve something, on the precise definition of a loop, on the precise definition of a variable, on the precise definition of how to print a value. The declarative program, on the other hand, focuses on what we want to achieve, with leaving the implementation details aside. We'll now go through key functional programming constructs in Scala, which are actually common to all modern functional programming languages. We'll cover immutability, pure functions, referential transparency, algebraic data types, pattern matching, and recursion. Starting off with immutable values, the main problem with variables is that they can be, changed anytime from any place that has a reference. This, in turn, can lead to unintentional shared mutable state, which is a huge problem in modern programming. Immutable values, on the other hand, cannot be changed. Instead of modifying the same memory location, we create new values. This essentially prevents from having any mutable state whatsoever. I find this to be a funny analogy, with immutable values being something like a Bruce Banner. He's clever, he can always provide you with ideas. He is essentially a way of reason. Variables, on the other hand, are something resembling Hulk. They are very powerful, they can do amazing things in terms of performance, but at the same time, they can cause destruction to your program that you're building. So what immutable values help you to achieve? Immutable values significantly reduce concurrency issues because no threads can be modifying the same value to instead be operating on these copies of the same value. Immutable values prevent shared mutable state from happening at all. And also they provide something called local reasoning, meaning that whenever you look at the value, you always know that no other thread is modifying it. And you are sure that what you see is what you get. The usual drawback with immutable values is extra memory allocations. since we are not modifying the same memory locations, we need to create new values, which results in a high memory throughput. However, as most applications nowadays are mainly concerned with having network calls or file operations, which take significantly more time than creating a single value, this shouldn't be a big issue. Moving on to pure functions. Pure functions embrace the property of being side effect free, meaning that everything that the function does can be observed in its return value. Pure functions are total. They return values for every possible input without throwing in an exception for an undefined input. They are deterministic, meaning that given the same inputs, they will return the same outputs every time. And they are locally scoped, which means they don't have any effect on the state outside of the function scope. However, all these properties can be merged into one called referential transparency. Referential transparency states that all calls to a function can be substituted with its return value. This property is essential for being able to reason about your program. If you cannot substitute a function call for its value, it means that you have to know the precise implementation of that function. And it becomes really hard to keep all the implementations of non-trivial functions inside your head. To give you an example, consider these two functions. getIt function is not referentially transparent because it returns a new value each time it's called, even given the same inputs. The increment function, on the other hand, returns the same value for the same input, but it has a very important side effect, which means we cannot just replace the function with its return value. The function on the right part of the slide, on the other hand, is totally referentially transparent, even despite using the mutable constructs inside it. All the mutation is scoped to the inside of the function, meaning we can safely substitute the packed function with its return value. The question that naturally arises is, can we create a useful program without any side effects? The answer is simple. No, we cannot, because we wouldn't be able to see the results, because even printing to a console is a side effect. However, we can significantly reduce the amount of side effecting code inside our programs. Instead of straightforwardly running side effects, we can describe side effecting computations. Then we combine all these descriptions in a single one and run the resulting computation in the main method. This means that the only side effecting part of our code would be the main function. To achieve this, we can use something called I/O, standing for input-output. This construct represents a computation, a description of the computation that will produce a value of type A. We'll get this value only when we explicitly run it. I'll illustrate this with an example. Consider these two functions. The first function saves a value to a database by a key, and the second one tries to get the value by a key. These functions do not perform the side effects immediately. Instead, they produce a computation of those actions. Then we can construct a program which first saves the value to a database and then tries to get a value by the same key. Because our functions produce a mere description, we can pass them through a rate limiting block, which will ensure that the database isn't called too frequently. This is the resulting program we get. Lastly, to run the program, we execute the run, sing, and save method. The very name of this method states that we shouldn't be doing that too often. Instead, it is really required. So to summarize, pure functions bring tremendous benefits. What we started with immutable values, bringing the local reasoning to values level, the pure functions extend, bringing that local reasoning to the computation level. You can now safely combine the function together and even call them in parallel, since you are sure they would not affect each other because they don't have side effects. This also results in much easier testing because each function becomes an independent unit. As a usual drawback, using pure functions usually results in extra object allocations, and to operate mutable state, you usually require something called an effect system on a language level, or a library to easily perform things that I/O does, for example. Otherwise, you'll be writing too much code for yourself, which is usually not a good practice. Moving on to algebraic data types. Algebraic data type is something that is essentially a product type or a sum type. We'll start with the definition first, and then follow up with an example. Product types define how to create a value, meaning that they define the exact fields that this value is supposed to have. Sum types, on the other hand, define the range of values without providing how to construct each individual value. Let's start with product types. On the left part of the slide, you can see a traditional class definition, class called person. This class has 3 constructors, and without looking inside the implementation, you cannot really say which of them is the primary constructor, if any. Also, it is very hard to tell if the constructors are really related. You have to know the implementation details to answer that question. However, with the product type, in this case written in Scala, you always have to provide the fields that define your data. In this case, we have 2 fields, age and birth year. We can provide as many supplementary constructors as we want, but they will still be referring to the core fields we defined. With product types, the intention becomes much more clear, and it's easier to understand the logic of the data. As with sum types, they are more closely related to interfaces. Suppose we have an interface called user, which we declare is public, and we have 2 implementations for it, client and admin. Despite having only 2 implementations, the function process cannot really say if a user that it gets is a client or an admin, because anyone could be implementing the user interface. This means that we always have to provide a default case or raise an error in case we do not know the type of the user we are getting. With sum types, we are actually able to limit the range of values we're defining. In Scala, it's done with using the keyword sealed, which states that all the implementations needs to be defined in the same file as the interface. Now, the function process gains the knowledge given to it by the compiler that the user can only be a client or an admin. This also gives the programmer guarantees for that the user can only be one of either a client or an admin, and significantly simplifies the implementation of the process function, and also reduces the scope of things that the programmer has to think about. What's more important, algebraic data types provide you with a feature called pattern matching. Since we know everything about how to construct a value, we can now reverse this operation and deconstruct all the values. Consider the definition on the left part of the slide. We are constructing a client and an admin, which are both users. Now, for the sample definition of a process function, we can just go over all the cases of what a client or an admin can be. Since we've covered all possible cases, we don't need to provide a default case. The compiler will instead issue a warning if we missed something. To summarize, algebraic data types and pattern matching significantly enhance the readability of your code, and also reduce the scope of things you have to think about. As an additional benefit, they provide some nice compile time checks, though exhaustiveness checks are not all powerful, but nevertheless provide additional safety. As again, usually using pattern matching results in extra object allocations because it has to construct some additional objects for checking the patterns you're providing, but still that doesn't seem to be a big issue in real-world applications. Lastly, let's go recursion. Given all the things we've covered, recursive functions become a very declarative way of writing programs, also given its mapping to many real-world problems. And despite common thinking, recursion can be almost as efficient as a loop, but only because the compiler will rewrite it to resemble the loop. In Scala specifically, if a function only returns a single value or the call of itself, it can be optimized by the compiler, so it only uses a single stack frame, meaning that it will not throw stack overflow errors if called too many times. On the right part of the slide, you can see a fold left function, which is one of the core functions for defining operations on lists. Such functions as map, filter, reduce, and others can be defined in terms of fold left. To summarize, this is the points we've covered. We talked about immutability and why is it important. We talked about pure functions and referential transparency. We talked about algebraic data types and their ties with pattern matching. And we finished with recursion. Now, let's go over some more Scala-specific features. These are not necessarily features unique to Scala, but they are not related to the core functional programming that we were covering in the first part. We'll talk about for comprehensions, hard-coded types, syntax extensions, macros, and implicit values in Scala. Let's start with for comprehensions. Suppose we have three functions which all return optional values. If your program is only concerned with the case where each of the values actually contains something, you can write it as a for comprehension. So in the example presented on the slide, we try to get a user by the username Jack, and then if the profile is defined, we'll fetch comments and a bonus defined for this profile. Then, if everything is defined, we'll take the first 10 comments and increase their rating by the bonus amount. You can see that this way of writing programs is very declarative, and it can be read very easily, even without knowing the language. Thus, for comprehensions define a very coherent syntax for sequential composition. They are essentially nothing but syntactic sugar for every type with map, flat map, and with filter methods. Thus, they can be used with any types applying these methods, even the type that you define by yourself. As a nice additional feature, you also take advantage of pattern matching, thus making your program even more declarative. Next, come higher-kinded types. Everyone is familiar with simple types, such as n, string, or a user from the previous example. But there also exist unary type constructors, or also known as generics, such as lists. They require a type parameter to be defined and used inside your program. We can require as many type parameters as we want, but they usually refer only to simple types. But what if we require a type to depend on a type, which in turn also depends on the type? Then we need to use higher-kinded types, which are best illustrated by the following example. Suppose we have a trait transformer, which for any given collection can transform the values inside it. The collection is represented by the type L, which itself requires a type parameter. Then, for any specific collection, we can call a run method, transforming the values inside it. As an example, we can create a transformer of lists, which simply calls the map method. This method, this transformer then can be run for any such collection, for any list. Higher kind types allow you to raise the level of abstraction where it's required, thus resulting in high code reuse. Next come macros. Macros are a somewhat experimental feature of Scala, which is designed to eliminate boilerplate code. Doing so at compile time, not at runtime. In the following example, we use Scala's JSON library called Cirky to provide a JSON encoder for a type foo. This JSON encoder can be easily defined by calling the derived encoder function, which is actually a macro that will construct an encoder at compile time. Such JSON encoder is a value that can be used inside of your program wherever you want. The next feature, implicit values, can be especially powerful in combination with macros. Implicit values are essentially a dependency injection mechanism on the language level, which is done at compile time. Consider the following example. In this case, we have the same class foo with an encoder defined as an implicit value. Then we define a process function which will require the encoder implicitly. Now, in any other part of the program, we can call the process function without providing the encoder explicitly, because it is defined as an implicit. While this example may be a bit too simple to fully cover the implicit, all the implicit features, I can assure you that it results in much more concise programs because there is much less code to read. Nevertheless, this feature is very powerful and can actually cause damage if used inappropriately or too much. Last but not least come syntax extensions. They are essentially built on top of implicits, and while definitely not being one of the major Scala features, I find them very convenient for increasing the readability of your programs. Syntax extensions allow you to create ad hoc methods for code reuse and readability. They can even be used on the types imported from other projects or libraries. In this example, we're creating a syntax extension for traditional Java strings. We provide an additional method called ASCII letters, which will filter any character from a string which is not from the ASCII list and which is not a letter. Thus, we have covered all the core Scala's language features. We've talked about for comprehensions, higher-kinded types, macros and their ties with implicit values, and we finished with syntax extensions. Now let's move into a more general topic. Again, talking about Scala as a language. We will talk about Scala's development and adoption rates, see its effect on productivity and performance. As I have stated, Scala has been around for over 15 years, but some still think that it is a relatively new language. Over these years, it has maintained a very intense release schedule. I think about at least two language improvements each year, while the same languages, such as Java, only provided one roughly every 2 years. The development of Scala is supported by the European government, which donated, I think, 1 million euros in 2012. And it is also supported by many major companies, such as Lightband, Twitter, Netflix, and so on. According to some sources, Scala is almost as popular as Kotlin for backend development, that is not considering Android applications, and is 15% more widespread in big companies. Stack Overflow survey in 2019 claims that almost 60% of developers that have tried Scala are interested in continuing working with it. And nowadays, approximately 4% of developers in the entire world use Scala as their main language at work. So the usage of Scala is not insignificant. There has actually been a survey asking Java programmers who have switched from Java to Scala in their work about the impact on their productivity and the time it takes for them to deliver the application to the market. And as you can see on this slide, most of them reported a significant productivity increase and reduction in time to market change. While these stats might seem a bit biased, they are actually supported by formal research. I was able to find two researches. The first one stating that Scala's functional programming style allows for writing 2 times less code, which unsurprisingly can be read 2 times faster, while the other one suggested that Scala projects, and I'm talking about the big, well-maintained Scala projects, need 30% less bug fixes than the average amongst all programming languages. This might seem like a marketing slogan, so I encourage you to read the research for yourself and see whether you agree with it. Scala being the JVM language, the main concern that comes about it is the performance. Many consider functional programming languages to be especially slow, but actually, compared to Java, Scala is not that slow. On the right part of the slide, you can see a graph comparing the collection operation calls both for Java and Scala. While in simple cases, Java is definitely the winner, in complex cases, Scala can Scala method runtime can be significantly faster than the Java ones. Not only that, Scala programs can also be compiled to a native binary, and the GraalVM website reports about 35% performance increase. Also, as for the build times, which is one of the main concerns with Scala again, it has significantly improved in the recent years, and utilizing incremental compilation results in only a few seconds delay per each build. To summarize, I would state that Scala as a language is quite rapidly developed. It is adopted by many big companies in the industry, and as suggested by both the survey and research, it can offer significant productivity benefits while keeping the reasonable performance. Now, moving on to Scala in real world, we'll cover the main areas of application and compare it with some other languages in the open. Well, because one of the main machine learning tools, Apache Spark, is written in Scala, unsurprisingly, one of the main use cases is creating data pipelines with Scala. This is actually one of the key reasons why it became popular. Nevertheless, Scala is widely used for defined resilient applications or distributed systems. If the application you're designing is small or rather simple, I don't think you would benefit with using Scala in your project. Also, if the domain you're operating on requires a lot of low-level manipulation, such as manual memory allocation or ensuring the precise assembly instructions, Scala is probably a wrong language for that. Lastly, if your project has a very simple backend, but heavily centers on UI, Scala is a wrong choice for that as well. Now, let's compare Scala and Java and Kotlin. While one of the biggest benefits of Java is its vast number of libraries for everything you can need, since Scala is fully compatible with Java and Kotlin libraries, Scala actually extends the ecosystem with its own libraries, which is definitely a plus. We have already established that in terms of performance, Scala and Java are relatively the same. So you wouldn't benefit much if choosing Java for performance concerns. However, while Java and Kotlin mainly focus on object-oriented approach, Scala allows for both functional programming and object-oriented one. So you can choose the one that most fits your needs at the given time. While I wasn't able to find any examples of Java and Kotlin targeting anything besides JVM, I know for sure that Scala can target JVM, browser, and native environments as its runtime platform. So if you need some flexibility in those terms, Scala can be definitely your choice. As Python one of the most widespread languages, especially for the machine learning purposes, it's natural to compare it with Scala. One of the key benefits of Scala in this case would be its native Spark and Hadoop integration. Well, because they are written in Scala, while Python, to my knowledge, allows only ad hoc integration with those tools. However, with Python, it being an interpreted language, it is very easy to prototype ideas to quickly verify your theory. While in Scala, Scala focuses more on compile time verification and resiliency to ensure that your application wouldn't fail in production. However, Python definitely wins in terms of number of math and visualization libraries because of its huge scientific history. Scala, on the other hand, can offer many machine learning-oriented libraries to process large amounts of data. This brings us to the last point. With Python, it is relatively hard to design pipelines that will operate on terabytes or even larger volumes of data, while Scala performs quite well on such volumes. And that's why it is widespread in machine learning community. Lastly, while perhaps a strange case to compare with, I decided to put a Golang as a comparison target because Golang is one of the main languages for developing microservices and distributed systems. Well, I would say that one of the key differences between Scala and Golang is that Golang is a very opinionated language with its fixed imperative style. Scala offers an extensible declarative style, which allows you to write, as stated, very concise and clear programs that are easy to understand. However, in terms of performance, Scala could not compare with Golang. It is blazing fast. But as we have already covered, for most programming tests and for large volumes of data, Scala can provide you with reasonable performance. The last point I would like to compare is that Golang focuses on concurrency primitives on the language level, known as Go channels, but it does not provide the scalability toolset you need right in the standard library. Scala, on the other hand, has all the tools and libraries for developing large distributed applications that are reliable to run in production. As for future prospects, the next major version of Scala is coming at the end of this year, and you can take a look at it on the link presented on this slide. There has actually been a conference recently where the creator of the language, Martin Edersky, has given an overview of the key changes in Scala 3, which have been nicely summarized in the picture presented on this slide. That concludes my talk. Thank you for your attention. If you have any questions, feel free to post them in the chat. And you can find me on Twitter, Telegram, and GitHub by the username given on this slide. Thank you.
Yeah, let's thank you, Anton, with another round of applause. Hey. So, Anton, it's not your first time giving this kind of talk, right? I feel like you're quite eloquent.
I'm sorry, could you repeat that?
I mean, is it your first time giving presentation in the public?
Not really. I have already given a similar presentation in Rakuten, though it was more, let's say, technical oriented.
I see. That's interesting. Do you actually using Scala at work in your company?
Yes, I'm somewhat using Scala at my work, though I'm becoming, let's say, a user of many languages now.
I see.
I've been tackling with Java, Golang, Python, I think almost any language in existence.
I see. And comparing with all of them, you still prefer Scala as your main language?
Yes, I would state that I adopted the following paradigm: is that firstly, you need to create a program that is easy to read and which is, let's say, correct. So you can easily verify that the program is doing what you intended for it to do. And then later on, when you see that there is a performance issue or something like that, then you can adjust your program or even rewrite it to a different language. But at first, you need to have something concise to start on.
Okay. Sounds interesting. And right now we're gonna collect some Q&A from the audience, and I already got one. There's one guy asking, does the underscore mean partial function? Probably in one of your slides there's like underscore.
Yeah, I think I understand what the person is referring to.
Right.
Yes, let me go back to, yeah, for example, this slide. The map function uses an underscore, which represents the parameter of the function that will be applied. The map function actually itself accepts a function. So the underscore is a parameter of this function that the map accepts.
I see.
We just don't need to define a name for this parameter because we are only using it once.
Okay, understood. So it's not actually the partial function, right?
No, this function is total, so it is defined for every value
Right.
it's given. Yeah, sorry if I wasn't clear on that.
Understood. Yeah. Okay, and then like inside the chat room, like I saw people like discussing about like adopting functional programming paradigm or because you mentioned about, for example, immutability is good, but some guy like mentioned although mutability is messy, but it can save your ass. And do you have any comment on this? Like, because in the real world, most of the time we are, it's kind of sometimes it's kind of hard to make everything immutable, right?
Yes, that is a very good question. So let's go over to my slide with mutability. Oh, where is it? Oh, sorry. I think I lost it. Well, anyway, when yeah, I think I found it. Yeah. So in this case, the transparent function actually uses mutable constructs, variables inside it. But it is totally fine since the scope of the function is relatively small and it doesn't propagate the mutability outside of the function itself. So if you use mutability, let's say locally, for performance reasons, it's totally fine. However, if you are using mutability to, let's say, if you're using mutable variables from different parts of the program, this usually indicates that something is wrong because when because when different parts of the program change the same value, it is very hard to predict its state in each given time.
That's true. That's true. Understood. All right. And I'm gonna start picking up some other questions from audience. Is it fine?
Yeah, sure thing.
Okay. There's one guy saying, I have heard this from a Java developer. Anything Scala and Kotlin have now, Java will eventually adopt. So he feels there's no necessities to use another JVM language. And like the audience want to hear your comments about this.
Oh, yeah, that is also one of the key features that Scala, let's say, implicitly has, because uh, actually the team designing it, designing the Scala language, I mean, it is designing it from the scientific principles of how a language should exist, while at the same time hearing the people's needs and adopting the construct that the developers need. So the uh, third version of the language, the Scala 3, it is defined on a more formal language called dot, which on the other hand is defined in terms of dot calculus. Why am I even saying that? I'm I'm saying that because Scala on its very core level is a more principled language. It is designed with the clear goal in mind. It is designed given some uh, facts, let's say from science, which allows it to be to express some constructs more naturally. Uh,
Mm,
so even those the features like pattern matching and the mutable values, they do not come only because the creator of the language thought that these features are cool or whatsoever. Uh,
mm,
there is a more complex path behind it to have a language that is both sound and easy to use. While
mm,
languages like Java and Kotlin, mm, I find them more chaotic. They they exist because somebody thought that like such an approach would be very convenient without having any real evidence to support that. Uh,
right.
So if you are saying that Java will eventually have all the features, it will only have them because like other languages have them, or because the there were requests from developers like please include this feature. That's why actually in the recent years the development of Java started accelerating, and we see 2 releases each year or whatever. But on its core level, it will still remain somewhat unprincipled, and you will find that constructs do not necessarily integrate very well with each other. While in
I
Scala,
see.
Scala was designed so each construct has a clear way to cooperate or integrate with others, uh, and this is one of the, I don't know, one of the core properties I would like to see in a language.
I see. I see. I think I got your point because I'm a front end engineer, right? And most of the time we are writing JavaScript. And one day, I heard a talk about Elm, which is also a pure functional programming languages. And I also asked like similar questions, like asking the speaker, right now JavaScript also incorporate like some other functional programming features into the language itself. And at the end of the day, is it possible like Elm doesn't have any position that it can still persist. And I guess the speaker also answered the similar answers as you, like saying like some language core features sometimes it's really hard to change. For example, JavaScript inherently it doesn't have types, right? So if you want to do things like pattern matching or some other stuff, it's kind of probably will be much more difficult.
Well,
Right.
to slightly expand on what you are saying, I think Elm and Scala are somewhat close in this sense, because to execute Scala programs, you need to compile them into Java's bytecode. So
Mm,
in the end, you are still running on the JVM with the same Java bytecode, but you have a more
mm,
principled structure on top with which you are directly cooperating, let's say. Same thing with Elm. It gets compiled to JavaScript because this is the thing you run inside browsers. But on the top level, you have a more sound, more principled structure.
mm. I see. I see. Yeah, that's interesting. Thank you for your answer. And we got another question from the audience. I don't really get the question, but the question itself is: I heard that Dati is quite divisive in the Scala community. And what are your thoughts on it? Does it make sense for a person to learn Scala, considering Dati comes out soon?
Yes. Yeah. Another, tricky, a bit tricky question, but I think it's a relatively good one to ask. Yes, Scala 3, also known as Dati, will be uh, introducing some new features while deprecating the old ones. So it will be maybe not slightly, it will be a relatively different language from what we know in Scala 2.
Mm,
However, to ensure a swift and convenient migration process, uh, in the first versions of Scala 3, almost all of the programs written in Scala 2 will be valid. The only feature that gets dropped are the macros. They are not dropped, I'm sorry, they are changed in a way that does not allow for their easy migrations. However, this is only this concern is mainly for the library designers, because usually the applications that use Scala, they only import macros from somewhere else. So you just need to change the library, or if the library provides an implementation for Scala 3, still like you are able to use the macro from that library. As for
mm,
the division of community, uh, I don't think I can rightfully comment on this topic, because I don't have the numbers of like who will switch to Scala 3 and who will remain on Scala 2. I
mm.
I still think uh, it's good to start learning Scala now, because all of the concepts you see inside Scala 2 will be implemented in Scala 3, but in a more principled and maybe slightly syntactically different way.
I
So
see.
there is a valid concern that Scala 3 will divide Scala community, but it definitely won't be the case as with Python 2 and Python 3, where there were like two communities existing in parallel.
Okay, okay. Thank you for your abundant answers. And I guess we don't have further questions. Um, Let me see. Ah, yeah, like one guy mentioned, because for some of your slides you're using ligatures, right?
Oh,
Yeah,
yes.
and for probably for some people unaware with the syntax, probably they will feel a little bit confused.
Oh, yes. I'm sorry. This is just the formatter I'm using for the slides.
Yeah,
Uh,
actually, I'm also using ligature. I can, yeah, I can get it.
this is one of the concerns that arose in early Scala days, when many libraries were taking use of ligatures and
Mm,
were programmers not familiar with them, it was quite hard to, write programs or use libraries using ligatures. But now it is just a formatting issue, not something that Scala really uses.
Right. Yeah, understood. I guess. Oh, there's one guy also mentioned. He doesn't see Java will having like things like pattern matching in the next 20 years. Oh, I guess this one is respond the questions like
Oh,
another audience asked. And you also answered as well, like even if Java kind of learn from other languages, and but for things like pattern matching, it's probably it will be a bit difficult for them to include in their next version.
if you'll allow me to expand on this topic, do I have some time for that?
Yeah. Go ahead.
There is a reason why Kotlin doesn't implement pattern matching in its full shape or form, because it actually has something resembling pattern matching, but it is not quite the same as in Scala. It doesn't have all the features. But the reason for it is because Kotlin developers, the developers of the Kotlin language, they do not want to make the language more complex. This is like their intent for the Kotlin to be as lightweight as possible. So they are not implementing pattern matching, even though it would significantly, let's say, improve the things inside of the compiler internally. They are keeping their pattern matching small because of that. And I think if Java and, well, maybe Kotlin will start to just integrate those features on top of language, not natively, because they were not designed in the view of them, they will eventually become something like C++, which has so many things on top of it. Like you just get lost when you start programming the language.
Like
This is also one of the concerns I have about Java, just getting on all the same features.
I see. Good to know. Okay, let's take our last question. Is it fine? The last
Yeah,
one.
sure. Yeah. Go ahead.
And one guy asked, like, what do you think about the trade-offs between implicit magic making code more convenient to write, but potentially way more difficult for people new to the code base to read and understand?
Yes, as I have stated, the implicits are one of the, let's say, controversial features. And at the conference I mentioned, the creator of the language, Martin Odersky, said that while implicits are very powerful, people are somewhat afraid to use them because they indeed can be hard to understand and hard to work with if they are used somewhat incorrectly. In the next version of Scala, this is getting improved. So the working with the implicits becomes more explicit. So there is slightly less magic involved. But at the same time, it still gets all the features, like all the powerful implicit features that we have in Scala 2. So I think that concern about implicits being magical and hard to use will be mostly resolved in the next version of Scala. I should state, however, that implicits are way less magical than using reflection or plugins that rewrite your program's bytecode, such as we see in Java. Because with implicits, you at least you get the error at the compile time, and you can also trace where the implicit error happened. While with reflection and with bytecode manipulation, you'll get errors in runtime that you have no idea how to deal with. So we can just take the less evil out of two.
I see.
Yeah, the lesser evil.
Okay. Yeah, I guess that's pretty much it about today's event. Thank you
Oh.
again for your impressive talk, and
Thank you so
hope we
much.
can see you again. And for our next event, we're gonna talk about Golang. And as you mentioned today, right? You also mentioned about Golang, and it's a good chance like next time we gonna have another talk talking about Golang, and like our audience can compare two languages together.
Sure thing.
And yeah, so because this is an online event, we can be like more chill and relaxing. What are you gonna do later? Are you gonna drink some beers or celebrating at home, things like that?
I think I'm just going to have dinner.
お疲れ様でした。Yeah.
ありがとうございます。
Okay. And oh, for our audience, can you guys fill in the survey? I guess we already posted the link in the chat, and I'm gonna show you this survey. And if you can, please fill in the survey. Your feedback will be really valuable to us because it's our very first event, and we want to improve our online event experience as well. And that's pretty much it. Thank you guys. Thank you guys for joining today. Anton, thank you. Thank you so much.
My pleasure. Thank you.
All right. And I'm gonna stop streaming. Can you say bye bye with me? All right. Bye
Bye
bye.
bye.
All right.